Okay, the next factor affecting melting temperature is interaction between the chain. Okay, a good interactions between polymer chains or between different segments of one and the same chain, such as dipole-dipole interaction and hydrogen bond, forms a strong hydrogen bond network throughout the whole material. In this polymer, the alkyl chain between the groups that operate either as donor or acceptor are of equal length and an ideal network develops. For example, polyamide, which is nylon 66, it melts at a temperature of roughly 267 degrees C due to the hydrogen bond interaction. While HDPE do not have the hydrogen bonding interaction, it melts at temperature as low as 137 degrees C. Okay, the other factor that affecting the melting temperature is the tacticity, so whether the arrangement of the polymer either isotactic, syntactic, or atactic. So as I mentioned earlier in our previous lecture, the atacticity polymers will generally be amorphous, okay, soft, flexibility material. So for isotactic and syntactic polymer will be more crystalline, thus harder and less flexible. Okay, so for example, we can see that the structure of polypropylene, atactic polypropylene, which has a random structure, it has very low melting point, and it is some gooey material. Okay, for isotactic polypropylene, it has high melting temperature as high as 176, which is in the crystalline state. It is also have a good material, and tough material that is very useful industrial. While for syntactic PP, it has similar properties with isotactic, but the condition is the appearance is very clear compared to the isotactic. So it is harder to synthesize for syntactic polymer. Okay, so the effect of the tacticity will play a very very main factors in affecting the melting temperature of the polymer. Okay, we look at the next slide. In terms of the branching, we can see that in the figure 5.4 show the influence of different branching of side chains on the melting temperature. As we can see that the Tm for the third structure here show the largest melting temperature compared to this both two compound. So we can explain, how can we explain about this? Okay, a compact branch side group generally leads to a stiffening of the polymer chain and create an increase in the melting temperature because of the effect that have been explained above in crystallization entropy. So actually the polymer with more branching, they will have more chain end, and if the branching is a short branching, it will reduce the Tg, but the different situation will occur depend on the side group of the branching and depends on the amount of the branching. Okay, if we have the branching side group which is large side group which contain for example aromatic chain or for example polystyrene or nitrile or chlorine. So this type of branching will increase the melting temperature. So in contrast to this, long flexible side chain will interfere with the crystal lattice and thus use the melting temperature to sink. An example of this can be found in the isotactic alpha polyolefin, where the melting temperature dropped from polypropylene to poly-1-pentene. Okay, we can see that poly-1-pentene show the lowest melting temperature compared to the polypropylene. Okay, initially the melting temperature it will continue to drop with the increasing of the side chain length. However, after a certain length, it increases again slightly. So this can be observed for side chain that are longer than 88 methyl units long, such as poly 1 lysine. And the reason for this is the increasing influence of the side chain to crystallize on the conformation of the main chain. Okay, branching is the main chain. Okay, branching in the main chain also leads to a lowering of the packing density. Okay, this lowers the crystallization enthalpy and thus also the melting temperature. Okay, we will look at the next factor. Okay, in terms of the molar mass. Okay, the end of the chain are, in comparison to the segment within the chain, relatively mobile. Okay, this mobility interferes with the crystal lattice and reduces the degree of crystallization. The resulting drop in melting temperature at low molar masses is a thermodynamic effect. This thermodynamic effect can, however, be superimposed by kinetic effect because polymer with very large molar mass will crystallize very slowly. It is possible, especially if the rate of cooling is fast, that polymer with high molar mass show lower crystallinity than their analogous of lower molar mass. Okay, table 5.3 lists the melting temperature of isostatic polypropylene of different molar masses. You can see that the polymer, the isostatic polypropylene with 3000 gram per mole molecular weight has the highest melting temperature. So we can conclude that polymer that have high ataupun rapid cooling, it will produce low crystallinity. Okay, rate of cooling is fast. The polymer with high molar masses show lower crystallinity. Okay, so kalau yang ni maknanya dia dah guna slow cooling lah ni sebab dia punya molecular weight dia tinggi. Molecular weight dia tinggi. Okay, for a low molecular weight chain, they will have more N per unit volume than the long chain. Thus, a higher free volume will produce a lower Tg. Okay, low molecular weight, dia akan produce lower Tg polymer. So, practically, the glass transition temperature value of a polymer is influenced by the molecular weight by up to 20,000. Okay, same goes to Tm. Okay, the next one is the co-monomers. Okay, most partially crystalline, which is linear homopolymer, are either characterized by a high melting temperature and a high glass transition temperature, or a low melting temperature and a low glass transition temperature. Okay, a rule of thumb is that the glass transition temperature is roughly 0.7 times the melting temperature. So the relationship is also valid for many small molecule substances in that they can also be converted into an amorphous state, such as in the pharmaceutical. Okay, most partially crystalline polymer are packed in an order fashion and have strong interaction between their polymer chains, and these properties will give rise to a higher modulus. Okay, thus rigidity, melting temperature, and glass transition temperature are usually closely related to one another. Okay, we will discuss about the Tm and the Tg. Okay, so the crucial fundamental idea here is that the crystallinity of a material is dependent on whether the chain segment in the crystal structure can arrange themselves in an order manner. whereas the glass liquid transition temperature is more dependent on how mobile the molecule in the polymer chains are. So we look at the figure, show the change in the Tm and Tg of two homopolymer, which is poly A and poly B, when their composition is gradually varied from 100% A to 100% B. The disturbance of the crystal structure, the melting temperature, okay, against the melting temperature here, it drops significantly, even if only relatively small amount of co-monomer are present. Alright. And the disturbance can be so strong in material where the co-monomer account for half of the composition that the material does not crystallize at all and remain amorphous. And the linear interpolation of the glass transition temperature is a simplification and generally only approach the real case when the co-monomer are chemically very similar to one another. And the effect of copolymerization on melting temperature can be approximately estimated, whereby, in the next slide, oh tak ada dah, okay tak apa. So we can see that the melting temperature of a copolymer, which is given by a TAB. Actually, there is no equation that I have mentioned earlier, so but it's okay. The equation show a more details equation that we explain about the graph, but it is okay. So the different variable that influence melting temperature mentioned in the graph above, responsible for the slightly different melting temperature listed in the literature for commercially identical polymer. Okay, so the difference can be ascribed especially to molar mass, the degree of branching, tacticity, and the thermal history of the material. Therefore, it is untrue that any one of the listed value is more or less correct than any of the others. Okay, let's look at the 5 distinguishable states in semicrystalline polymer can exist when the elastic modulus is measured over a range of temperature. So we have the glassy state, leathery or glass transition state, the rubbery plateau state or rubbery state, rubbery flow, and also the viscose state. Okay, this is the dependence of relaxation modulus on the temperature. So the glassy state is a state that happened in this area, and the TG is in the center of the decline state here. Rubbery state is here, rubbery flow is here, and last one is the viscose flow. Okay, in the glassy state, here the modulus is high and the polymer is hard and brittle. So polymer is here is in the hard stage, hard formation. Okay, we have seen that in the glassy state, in the chains are frozen in position and molecular motion is restricted to vibration. And in the glass transition state, okay, whereby the modulus decreases by 3 order of magnitude, close to Tg, the molecule have acquired enough thermal energy to overcome the potential energy barrier. At this stage, long-range coordinate motion of 10 to 50 degree atoms can take place. So at the glassy state, we can say that the atom or molecule get the energy and it rotates at its position. Okay, during the rubbery state, as temperature increases, the modulus approaches a constant value. Okay, we look at the rubbery state. Okay, so reaching a plateau. Okay, in this temperature range, the chains are considerably entangled, but the chain segments are very mobile. Okay, so the length of the rubbery plateau region depends on the molecular weight and also the cross-linking. Okay, in the rubbery flow, the chain have acquired higher thermal energy, slippage may take place, hence flow, and the large stage is the viscose flow, whereby at high temperature, the entanglement no longer act as physical constraint to the translation motion, and chain can slip past one another, and the sample now flows as a liquid. Okay, we have end our chapter 1. Okay, thank you.